Okay, today we are going to look to an example of the application of the Fourier series, and this example will be useful to explain a very famous phenomenon that is regarding the Fourier series. Okay, so we are going to start by a function f of x, and we are going to find the development in signs of this function. And this function is going to be defined as -1 from negative pi to 0 and 1 from 0 to pi. Okay, so the graph is very easy to find. We are going to have something like this. Okay, this will be 1 if pi is over here and -1 if negative pi is over here. Okay, this will be the graph of the function. So what we are going to do is to express this function in terms of its Fourier series. Okay, perfect. So just let me remember that, well, we have made a video explaining how to get the Euler Fourier equations that are necessary to find the constants that will be involved in the Fourier series of the function. Okay, so those equations are the next. Okay, perfect. These are the Euler Fourier equations that we need to solve first. Okay, so we are going to begin with the easiest one, A0. Okay, in this case we need to identify that the p is, well, equal to pi. Okay, because the interval where we are taking the function definition, well, is from negative pi to pi. Okay, perfect. So A0 is going to be, well, 1 over pi, the integral from negative pi to pi of, well, f of x dx. And looking at, well, the function is defined in two ways depending on the side of the interval we are located in. Well, we need to split the integral into two pieces. This is going to be 1 over pi, the integral from negative pi to 0, and in this interval of integration the value of the function is -1, and we are going to integrate on the variable x. And the second piece is going to be 1 over pi, the integral from 0 to pi of 1 dx. Perfect. Okay, so if we solve this, well, it's a very easy integral. We are going to get 1 over pi times negative x from negative pi to 0, and then plus 1 over pi, the x from 0 to pi. Okay, so it is very easy to notice that, well, this is going to be -1 plus 1, which is going to be, of course, 0. Perfect, so right now we are going to start with the a sub n term. So that is going to be 1 over pi times the integral from negative pi to pi, or let me split this from the beginning. This will be from negative pi to 0 of, well, -1 times cosine of n pi x over p dx plus the integral from 0 to pi of 1 times cosine of n pi x over p dx. Perfect. So this is going to be, well, and actually, well, remember that these p's are pi. Okay, so looking that we have a pi divided by pi, pi divided by pi, well, we just get a cosine of n times x. Okay, so when we take the integral, we are going to get something like sine of nx, okay, times maybe a constant. But the important thing here is that, well, looking that our limits of integrations are negative pi and 0, well, of course, the sign evaluated at 0 is 0, and evaluated at a multiple of pi is also going to be 0. And that same thing will happen in this integral. So that means that these two terms are going to be equal to 0. Okay? Again, because we get a sign, and this sign is evaluated in pi and in 0, so that is always 0. Perfect, that was very easy. So we are just now going to get a b sub n term that we need to calculate as 1 over pi times the integral from negative pi to 0 of negative 1 times sine of n pi x over pi again dx plus 1 over pi the integral from 0 to pi of sine of n pi x over pi dx. Again, these pi's can be cancelled. Okay, so if we take the integral of sine of nx, well, of course, we are going to get that this is 1 over n cosine of n times x, and well, the derivative of the cosine is, well, negative sign, but remember, well, here we have a negative, so the entire result of this integral is this. Okay, perfect. And in this case, well, it will be like the same, but instead of negative, it will be positive. So we are going to get a negative cosine of n times x here. And of course, divided by n. Perfect. So if we rewrite this, we are going to get that b sub n is equal to 1 over pi times 1 over n. And we can take that factor out, so we are going to get 1 over pi n times cosine of n times x from negative pi to 0, and then plus, well, actually minus cosine of n times x from 0 to pi. Perfect. Okay, so we are going to get 1 over pi n times cosine of 0, which is going to be equal to 1, minus cosine of minus pi n, and then minus cosine of n pi, and then plus, because with this minus, and well, the minus of the fundamental theorem of calculus will be a plus, so cosine of 0. Okay, cosine of 0 is equal to 1, and we have our 1 here. So we are going to get 2 if we sum this with this. And remember that the cosine, well, is an even function. So a property of even functions is that if you have f of minus x, this is equal to f of x. So this cosine of negative pi n, well, is going to be equal to cosine of pi n. Okay, and well, it's the same of this, so we are going to get negative 2 cosine of pi n. So we are going to have a common factor of 2, and we are going to take that out of the brackets to get 2 pi n times 1 minus cosine of pi n. Perfect. Okay, so what happens with this quantity that we have here? Well, remember that the n begins in 1 and it keeps going from 1 to infinity. So, for example, if we take n equals to 1, well, we are going to have cosine of pi, and that is, well, negative 1. Okay, if we take n equals to 2, we are going to get cosine of 2 pi, but that is equal to 1. So we are going to be oscillating between negative 1 and 1. So that means that, well, cosine of pi n is going to be equal to negative 1 to the n. Okay, if we want to calculate, for example, the n equals to 3 term, this will be cosine of 3 pi. Okay, but remember that if we are in the plane here, cosine of pi is like calculating cosine of this angle over here, because this angle represents pi. So cosine of 2 pi is like calculating again cosine of 0, so that's why cosine of 2 pi is equal to 1. And cosine of 3 pi will be to be again in the cosine of pi situation. Okay, so that's why this is going to be equal to negative 1. Okay, so again, we oscillate in negative 1 and 1. Okay, so we can rewrite this as 2 over pi n times 1 minus, well, negative 1 to the n. Okay, we could take this negative 1 and, well, write this as 1 plus negative 1 to the n plus 1 maybe, but we are going to leave this expression as that is. Perfect. Okay, so now we are going to write the Fourier series of the function f of x. Remember that the Fourier series included the terms a0, b sub n, and a sub n, but we have calculated that this is equal to 0 and this is equal to 0. And the b sub n term, remember, well, is like the next. We had that f of x is equal to well, the sum from n equals 1 to infinity of b sub n sine of n pi x over p, where remember p here is equal to pi. But yeah, because the other terms have been gone to 0. Okay, perfect. So that means that, well, our function can be written as well, the sum from n equals 1 to infinity of 2 over pi n 1 minus 1 to the n sine of n pi x over pi, and, well, these can be cancelled, so we get that this is sine of nx. Perfect. Just to rewrite this, well, we can take the 2 over pi out, and the sum from n equals 1 to infinity of 1 minus 1 to the n over n sine of n times x. Perfect. So this will be the Fourier series of the function f of x that we are dealing with. Okay, so right now what I'm going to do is to show you 4 cases of the graphs of this function, where, for example, we take not the limit to infinity, but we take, for example, these up to 1, 2, 3, and 15. Okay, so we are going to take like the partial sums of the function just in these 4 cases to see how the graph is. And remember that the Fourier series consists in that, well, when we take these limits up to the infinity value, well, this function f is going to be exactly equal to the Fourier series. Okay, but of course, looking that we are taking finite limits in these examples, well, the function f cannot be seen as exactly the same. Okay, so let me show you the graphs. Okay, perfect. This will be the graphs of the function f of x in partial sums. Here we are taking the limit equals to 1, to 2, to 3, and to 15. Okay, remember, when we take the limit of the n up to infinity, we are going to get exactly this, the function f. So look that when we increase n, well, the function turns out to be similar to the function f. Remember that f has this form over here. So again, when we increase the quantity of sums on the Fourier series, the quantity of terms in the Fourier series, well, the graph is going to be more and more similar to f. Okay, if you see, well, in y equals to 1, well, this turns out to be more and more similar to the function f. Perfect. But what I wanted to mention in this video, which is the important part of the video, is that it turns out that in some Fourier series, for example, in this one in particular, it turns out that when n tends to infinity, okay, if we keep increasing the terms on the Fourier series expansion, we are going to look to a very curious phenomenon that occurs when f has discontinuities. Look here the way we have defined the function f. it is not defined at the terms x equals to 0, x equals to pi, and x equals to negative pi. Okay, in those points, well, the function is not defined. That means that we have discontinuities in x equals to 0, x equals to pi. This will be the point pi, and this negative pi. So what happens when this function turns... So what we look in this case where the function has a discontinuity, we see that there are some peaks on the function. Okay, here we have a peak, and here we have another peak where we have the discontinuities. And this phenomenon is known as the Gibbs phenomenon. Well, it turns out that when we increase n more and more, well, the Gibbs phenomenon turns out to be more and more visible. If you see, for example, the other graphs, you see that when n is equal to 2, well, the Gibbs phenomenon doesn't appear at all, actually. So yeah, for example, where n is up to 3, here maybe, well, we start noticing a little bit of the effect of the Gibbs phenomenon, maybe, but not that much. For example, we take the n equals to 15 case to start noticing that, well, the Gibbs phenomenon appears, and, well, it's very remarkable in this case. Okay, so these peaks, again, they only appear at the points of discontinuities. Okay, perfect. So that is the concept that I wanted to show in this video, because it will be very important, for example, in the analysis of image processing in engineering, maybe. And in all Fourier analysis, well, it is indispensable to know what is the Gibbs phenomenon. Perfect. So this will be a very good point to finish the video.